Okay, I'm going to talk through real quick our Sig-Fig rules that we covered in class on Thursday. Now, one of the things I want to make sure that I mention here, Sig-Figs, when we talk about Sig-Figs, we're not talking about important numbers. We're talking about how reliable those numbers are. When you get right down to it, Sig-Figs or Sig-Fig rules are just a list of very specific rounding rules that we're going to use. Now, there's three kinds of significant numbers. There's measured numbers, calculated numbers, and integers. On measured numbers, that's the main thing we're going to be talking about. How to determine, looking at a measured number, how many sig-figs it has. Later in the class, when we're actually taking measurements, we'll talk about how to determine how many sig-figs you should get. But right now, I just want you to be able to look at a measured number and determine how many sig-figs it has. So, here are some of your more important rules. For any measured number, which includes decimals, all of the decimals are considered significant. I want to make a clarification here. All of the non-zero decimals are significant. Sometimes zeros are significant, sometimes they are not. We'll talk about that a little bit more here in a second. Whenever a number includes digits which are not significant, the last sig-fig should be underlined. If there are no underlined numbers, then all digits are to be considered significant. So in these first five, the only two numbers that are might include insignificant digits are these two. This one, and this one are all non-zero digits, so every digit here is significant. For zeros, when zeros are between two other sig-figs, they are considered significant. So this 0 is between the 2 and the 4. This 0 is between the 2 and the 8. So both of these would be considered significant. So 27 would have 2 sig-figs. 379 would have 3. That number would have 6. And the last two would be 4 and 3. I don't think anybody had any trouble with those. Sometimes zeros are used as placeholders, and these are probably the ones that people are the most frustrated by. Because identifying placeholder zeros can be a little tedious. So first and foremost, the thing you have to keep in mind is leading zeros are never significant. Never are leading zeros significant. So a leading zero is going to be a zero that comes before the digits of your number. So in this number, this 0 is a leading 0. In this one, all 4 of these are leading zeros. These 3, these 2. This one shouldn't be there. It makes no sense for this 0 to be here, so ignore that one. But all of these zeros are leading zeros, so they are not significant. They do not count as sig-figs. And so these all would have 2, 1, 2, 3, and 3 sig-figs. Next, let's talk about the placeholder zeros that may or may not be significant. Sometimes a placeholder zero is actually a sig-fig, or a zero that could be a placeholder zero is actually significant. Now, the same rule still applies here. Leading zeros are never going to be significant. It's trailing zeros that are sometimes significant. So in this number, these 4 are leading zeros. These 2 are trailing zeros. So in this number here, whenever we have significant, or whenever we have a number that contains both significant and insignificant digits, that is, other than leading zeros, we underline the last sig-fig so that we know it is the last sig-fig. So in this number, by underlining the 8, we're stating that this 3-digit number only contains 2 sig-figs, the 2 and the 8. While in 7,000, we have a 4-digit number, but since the middle 0 here is underlined, this is a sig-fig. The fact that this is underlined makes this a sig-fig. 7 is significant. This 0 is significant. That means this 0 is also significant. So this is a 3 sig-fig number. Now, trailing zeros, though, can be on both sides of the decimal point. So up here, we precede the decimal point. We are to the left of the decimal point, because the decimal point would be right here. But in this number, we are after the decimal point. So this 0, this is a trailing 0, but how do we tell whether it's significant or not? Because we never underline anything after the decimal point. To tell, you simply look at it and go, would I write that 0 for any reason other than if it was significant? Would you write this 0 if it wasn't a sig-fig? And the answer is no, you wouldn't. When we start doing calculations here in a bit, you'll see in the next video where we'll probably have a situation where we do a calculation and we get a 2-digit number, but we need 3 sig-figs. So what we do is we add a 0 to the end to keep that sig-fig. And then this one here, leading zeros are never significant. These 2 trailing zeros were after the decimal point, so these 2 trailing zeros have to be significant or they wouldn't be written. So 2, 3, 3, and 3. Now that's most of the really important rules. So from here, I've got some practice numbers here. So pause this for a sec and identify how many sig-figs are in each of these. Okay, now I'm going to go through them. Okay, the first one, 27, we have 2 digits. Neither of them is a 0, so both would be significant. So 2 sig-figs. Same here, but 3. Here we have a 4-digit number. 2 of them are zeros, but those 2 zeros are between 2 other sig-figs. So this is going to be 4 sig-figs. 0.054, leading zeros are never significant, so this is 2. 2.00, those zeros are after the decimal point. We would not have written them unless they were significant. So that one's going to be 3. This one, we have 3 leading zeros, which are never going to be significant. And then at the very end, we have a trailing 0. After the decimal point, it has to be significant. So that's going to be a 3-digit, or a 3 sig-fig. And then the last one, this one's kind of up in the air. But this 0, because this 0 is after the decimal point, this 0 has to be significant. This is a non-zero, so this is significant, which means that this is a 4 sig-fig number. So that's identifying how many sig-figs are in measured numbers, or at least looking at a number and saying, how many sig-figs does this number have? This is how you would do that. The next step in this are our calculated numbers. So in calculated numbers, you take measured numbers and you're performing calculations with them. Usually it's going to be multiplication, division is going to be the main one that we're going to talk about. No calculated number can be more precise than the measured numbers you started with and retain its viability. That is, and retain its reliability would be another way to say that. Calculated numbers cannot have, that's a typo, cannot have more sig-figs or significant digits than the measured numbers you started with. No calculated number. Oh, there we go. Okay. No calculated number can have more sig-figs than the measured numbers you started with and remain accurate. That's correct. Okay. So, therefore, any calculated number, multiplicative, that means multiplying, using that number was gotten by multiplying or dividing, must be rounded to the same number of digits as the numbers you started with. If the numbers you started with have a different number of sig figs, then the calculator should have the same number as the lowest number you started with. So, for example, if you take a 3 sig fig number and multiply it by a 2 sig fig number, the answer can only have 2 sig figs. It can never go up. You cannot get a 3 sig fig answer from that calculation. So, for a quick little example here, if you multiply, if we take 27.38 times 15, this is a 4 sig fig number, this is a 2 sig fig number. That gives us 410.7. This is a 4-digit number, but we can only have 2 sig figs. So we have to round 410 to 2 sig figs. So we start counting with the 4, 1, 2. This is our last sig fig. So we have to underline this number because we are before the decimal point. 0 makes this 1 stay the same. It doesn't go up. And then the rest of these become zeros. So the 7 becomes a 0. Because it's after the decimal point and it's not significant, we drop it, which gives us, as a final answer, 410 with the 1 underlined. So this is a 2 sig fig number, and this would be the 2 sig fig version of this number. So then a couple other practice problems. 7 times 7 is normally 49. Okay, but 7 and 7 are both 1 sig fig numbers, which means this number can only have 1 sig fig. So this is going to be our last significant digit, our first number. 9 makes the 4 round up to a 5, so this becomes a 5. The rest of these become zeros. We have only 1 sig fig, so we have to underline the last one. So that would be 50. Whereas 7.0 times 7.0, we have 2 digits in both of those numbers, 2 sig figs, so that would actually stay as 49. And we don't have to round anything because we've got the correct number of sig figs. So go ahead, run through the rest of these. I'll go through them in just a second. Pause the video if you need to because I'm about to start. All right, hopefully you pause that. You've got answers. Let's go through these. 3 digits times 1 digit. If we multiply those out, we're going to get 1,780. But 1,780, we can only have 1 sig fig because of the 5. So 1 would be our last sig fig. 7 makes the 1 become a 2. That's our last sig fig. The rest of these become zeros, which is how we get 2,000. Okay, then we have 3 sig figs times 2, so our answer can only have 2 sig figs. We get a 5-digit number out of the calculator. We have to round that to 2 sig figs. This 2 here makes this 2 stay the same. So we underline this 2. The rest of these become zeros. Technically, this would be 0.00, but since those 2 are not significant, we drop them. They go away. So this would be our answer. 300 times 150. This has 2 because of the underline. This has nothing underlined, so this one is 3. So when we multiply those out, we get 45,000. We only need 2 sig figs. As it just so happens, the 5 is the last sig fig, and everything else is already a 0. So we just underline the 5, and that one is good. 30.0 times 0.050 gives us 1.5. We have 3 sig figs here, but only 2 here. So we have 2 in our answer. So we don't have to do any rounding on that one. We can only have 1 sig fig in this one. So 242.7 becomes 200 with the 2 underlined. We can only have 2 in this one. So, wow, that's a bit of a typo there. So right here, there should be some spaces. So 105.087 becomes 110 with that second 1 underlined. 8 times 9, 72 becomes 70. And with these two, we have a 2-digit and a 3-digit. So our answer can only have 2. Again, we do not underline the last digit because it's after the decimal point. And then here, we take 3-digit times a 2, 3 sig fig times 2. So we can only have 2 sig figs in our answer. So we underline the first 0. So hopefully that helps with calculated numbers. We will be dealing more with those as we move forward in the unit. The last thing I want to talk about is integers. All right, integers have an infinite number of sig figs. So in particular, it talks about here subscripts and coefficients. That's more of a chemistry thing. I want to point out some of our equations. So if we look at two of our kinematics equations, we have VF squared equals VI squared plus 2AS, and S equals VIT plus AT squared over 2. This 2 and this 2 in this equation, or in these equations, those are both integers. Both of those are considered integers. So this has an infinite number of sig figs in it. Or it could be written as 2.00, or it could be 2.000, or 2.000000000000000. However many zeros you need, this has the correct number of digits. Now this is important because let's say we have 2 sig figs. That's bad, not there. We have 2 sig figs here, 3 sig figs here, and 4 sig figs here. So 3 in the A, 4 in the S, 2 in the VI. This could have as many sig figs as we need it to. Now, unfortunately, this is kind of a bad example because this one only has 2 digits. Or if this one only has 2 sig figs, then we can only get 2 sig figs out. But if this one was 3, even though only 1 digit is written here, this can be written as a 3-digit number. So this would be a 3 sig fig version of that 2. Same down here. We can have as many sig figs as we need it to. Okay, because it is exactly 2. The other thing I want to really mention, and this is something I did not mention in class, which is why I'm adding this in here. Unit conversions. In a conversion factor, all sig figs are significant. So, for example, let's use this one here. 1 inch is equal to 2.54 centimeters. Based on what we talked about with the measured numbers, this has 3 sig figs, this has 1. That's a serious problem because that means if we ever use this conversion factor, that we can only have one significant get out as the answer. But these two numbers are actually integers because they are exact. There is exactly 1 inch. There is 1 point infinite zeros inch in 2.54 centimeters. It is exact. That is why I told you you cannot use the shortcuts. These are integers. This is not. 1 foot equals 3.28 meters. Those are not integers because those are rounded. This is exact. These are integers. These are rounded. So this only has 3 sig figs. That's why I said not to use those conversion factors. Only use the ones that I gave you on that sheet, or the ones that we've talked about in class, because those shortcuts have rounding error, which is why we don't use them in here. That should be everything. I'm going to stop this one, and then I'm going to record a video going over one of those extra problems, the speeder problem here. So hope that helped.